So in this video we will discuss about the Laplace transform of some functions. As we know, given a function, say f of t, its Laplace transform is given by e to the power integral 0 to infinity e to the power minus st ft dt. So Laplace transform is defined on the variable s. So we will denote it by f of s. So here we will use big F and the function is denoted by little f. Okay, so the first function that we will consider is called unit step function. So this function is defined as, we will denote it by ut. It is defined as 0 when t is less than 0 and 1 when t is greater than 0, greater than or equal to 0. So if you look at the graph of this function, it will look like this. Up to 0 it is 0 and from there it is equal to 1. So here is 1. Okay, so this is the graph of the function ut. Okay, now we will substitute here. So f of s is equal to integral 0 to infinity e to the power minus st ft is equal to 1 when t is greater than or equal to 0. So 1 dt. Integrating, we will get e to the power minus st divided by minus s is the integral over the range 0 to infinity. So when you apply the upper limit, you will get 0, and when apply the lower limit, you will get 1. So the answer is equal to 1 by s. Okay. So the Laplace transform of unit step function turns out to be equal to 1 by s. Now there is a concept called inverse Laplace transform. So that we will denote like this. We will say f of t equal to L inverse of f of s. This means that the inverse Laplace transform of the function f of s, which is a function in the variable s, is equal to f of t. So since the Laplace transform of the unit step function is equal to 1 by s, the inverse Laplace transform of the function 1 by s is equal to the unit step function. Okay. The next function that we will discuss is called Dirac Delta function. Its definition is here. It is defined as equal to plus infinity when t is 0 and 0 when t not equal to 0, and there is also one requirement that the area under the graph of this function is equal to 1. So what is the graph of this function? It is equal to 0 when t not equal to 0, and at t equal to 0 it has got a very huge jump, and the jump is like that, the area is equal to 1. So it seems a little bit unbelievable that this function exists. So let us consider an approximation of this function. So here is minus a by 2 and here is a by 2. Now consider this function. So this height is equal to 1 by a. So it is defined as, the function is defined as f of t equal to 1 by a and minus a by 2 less than or equal to t less than or equal to a by 2 and 0 elsewhere. This is the definition of the following function, and you can see that the area under this curve is a rectangular area whose width is equal to a and length is 1 by a, so the area is equal to 1. Now you tend a to 0, so you can see that the width getting reduced and the height increases. So limit of this function turns out to be as a tends to 0. When a tends to 0, this function tends to the so-called Dirac Delta function. This is one such approximation. There are many other approximations of this Dirac delta function. So we will imagine that such a function exists. This function has one more important property that says integral of minus infinity plus infinity delta t f of t dt, that is equal to f of 0. Okay, so that is an important property that you have to remember. Now we will find out the Laplace transform of this function. So what is L of delta of t equal to integral 0 to infinity. Okay, so delta t e to the power minus st dt. Now we can extend this into integral minus infinity plus infinity delta t e to the power minus st dt, because delta t is 0 over the range minus infinity to 0. And when we apply this property here, in the place of f of t we have e to the power minus st, and therefore this is equal to e to the power minus s into 0 multiplied by 0, that is equal to 1. So the Laplace transform of the Dirac delta function is equal to 1. Now what is the inverse Laplace transform of 1? It turns out to be the Dirac delta function. So L inverse of 1 equal to delta t. The next function that we will consider is defined as follows. F of t is defined as 0 when t is less than 0, e to the power minus at when t is greater than 0. So in short, we can define this function as f of t equal to ut e to the power minus at. So the step function ut can be applied for defining this function. Instead of this definition, we can define it like this. Then Laplace transform of ft equal to integral 0 to infinity e to the power minus at e to the power minus st dt. So we can combine these terms here. There is 0 to infinity e to the power minus of a plus s t dt. The integration gives integral minus a plus s t divided by s plus a, 0 to infinity, minus is here. So that is equal to 1 by s plus a. So the Laplace transform of ut e to the power minus at is 1 by s plus a. Laplace transform of ut e to the power minus at is equal to 1 by s plus a. And therefore inverse transform of 1 by s plus a equal to ut e raised to minus at is the inverse Laplace transform of 1 by s plus a. Okay. The next function that we will consider is f of t equal to ut sine omega. Now we have a result that is called de Moivre's formula, which says e to the power I omega t is cos omega t plus I sine omega t. So e to the minus I omega t is cos omega t minus I sine omega t. So if we subtract, then you will get e to the power I omega t minus e to the power minus I omega t equal to 2I sine omega. From that, we can write sine omega t equal to e to the power I omega t minus e to the power minus I omega t divided by 2I. So we will make use of this expansion for finding the Laplace transform of sin omega t. Therefore, L of f of t equal to integral 0 to infinity e to the power I omega t minus e to the minus I omega t divided by 2I e to the power minus st dt. Okay. So that is equal to 1 by 2I e to the power minus s minus I omega t minus e to the power minus s plus I omega t dt. So a little bit of adjustment is done here. These two terms we have written like this. Integration gives e raised to minus s minus I omega t divided by minus of s minus I omega 0 to infinity minus e to the power minus s plus I omega t by minus of s plus I omega 0 to infinity. So on applying the limits, we will get 1 by 2I. Here it is 1 by s minus I omega minus here will be 1 by s plus I omega. So we can take the LCM and obtain 1 by 2I s plus I omega minus s plus I omega divided by s square plus omega square. So here we are using a plus b into a minus b. So it is a square minus I square omega square, but I square is minus 1. So this becomes s square plus omega square. So s gets cancelled. So this is equal to 2I omega divided by 2I multiplied by s square plus omega square. So 2I gets cancelled and we have Laplace transform of ut sin omega t is equal to omega divided by s square plus omega square, and hence the inverse Laplace transform of omega by s square plus omega square equal to ut sin omega. The next function that we will consider is f of t equal to ut cos omega t, or we will simply write it as cos omega t. Now proceeding as in the case of sin omega t, we can write cos omega t as equal to e raised to I omega t plus e to the power minus I omega t divided by 2. Okay. Hence, making use of this identity, Laplace transform of cos omega t is equal to integral 0 to infinity e to the power I omega t plus e to the power minus I omega t divided by 2 multiplied by e to the power minus st dt. So, little bit of adjustment, integral 0 to infinity e to the power minus s minus I omega t plus 1 by 2 is here, e to the power minus s plus I omega t dt equal to 1 by 2 multiplied by e to the minus s minus I omega t divided by minus s minus I omega 0 to infinity plus e to the minus of s plus I omega t divided by minus of s plus I omega over the range 0 to infinity. On applying the limits, we will arrive at this step, and on simplification, we will find out that the Laplace transform of cos omega t is s divided by s square plus a square. And hence we find out that Laplace transform of cos omega t is s by s square plus omega square, and the inverse Laplace transform of s by s square plus omega square is cos omega t.